Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at Born-Haber cycles. We're going to talk about what Born-Haber cycles are, why Born-Haber cycles can be useful, and show, using sodium chloride as an example, how we can use Born-Haber cycles to find lattice enthalpies. Hess's law and Hess cycles and lattice enthalpies have been covered in separate videos. Check the links in the description below. Before we talk in detail about Born-Haber cycles, there are a few essential ideas you need to be comfortable with. Enthalpy change refers to the change in heat energy of a system or substance during a reaction or process, measured at constant pressure. It is shown as delta H. Standard enthalpy changes are used to ensure enthalpy changes can be compared for different reactions and processes. A measured enthalpy change can be considered standard if standard conditions are used and reactants are in their standard states. Standard conditions are 298 Kelvin and 100 kilopascals. Standard states are the physical states of substances when they are at standard conditions. Hess's law tells us that the overall enthalpy change for the conversion of a set of reactants to products is the same regardless of the route taken, assuming initial and final conditions are the same. It is possible to find the enthalpy change for a part of a route if all other enthalpy changes are known. This can be done using Hess cycles. Hess cycles are useful to help find the enthalpy change of a reaction that can be hard to measure experimentally. For example, enthalpies of formation. Ionic lattices form by the attraction of oppositely charged ions to each other. Lattice enthalpies of formation refer to the enthalpy change that occurs when a lattice is formed from its constituent gaseous ions. Standard lattice enthalpies of formation refer to the enthalpy change that occurs when 1 mole's worth of an ionic lattice is formed from its constituent gaseous ions under standard conditions. As energy is always released when lattices form, lattice formation is exothermic, and lattice enthalpies of formation are negative. Breaking apart a lattice is endothermic, meaning lattice enthalpies of dissociation are positive. The value for both enthalpies is the same for a given lattice, the only difference is the positive and negative. Recap done? Let's go! Lattice enthalpies of formation and dissociation are impossible to measure experimentally. To keep the constituent gaseous ions separate at a constant temperature and pressure, mix them together perfectly, and then measure the enthalpy change that occurs when they combine to form a solid would be practically unachievable. It is possible, however, to find lattice enthalpies of formation indirectly using a particular type of Hess cycle called a Born-Haber cycle. A lattice doesn't have to be formed from its constituent ions in gaseous states. A lattice may also be formed by simply reacting the elements that make up the compound. This is referred to as an enthalpy of formation. Note that it is not a lattice enthalpy of formation, just an enthalpy of formation. If standard conditions are used and the elements are in their standard states, the enthalpy change would be a standard enthalpy of formation. We will summarize the definitions for standard enthalpy changes used later in the summary of this video. This means then that we have two ways we can form an ionic lattice: from gaseous ions, lattice enthalpy of formation, or from their elements in their standard states, enthalpy of formation. For many lattices, this enthalpy of formation is easier to measure experimentally. To find the lattice enthalpy of formation, all we now need to do is find the enthalpy change that occurs when you go from the constituent elements in their standard states to gaseous ions. Then we have a simple Hess cycle. There are two possible routes to go from the constituent elements to the lattice, route 1 and route 2. Hess's law tells us that the energy change that occurs for the formation of a product from a set of reactants is independent of the route taken, meaning route 1 equals route 2. In this case, that means route 1, enthalpy of formation, so from elements to lattice, equals the enthalpy change to turn the elements into gaseous ions plus the lattice enthalpy formation, forming a lattice from gaseous ions. Rearranging this means lattice enthalpy of formation equals enthalpy of formation minus the enthalpy change to turn the elements into gaseous ions. Lovely and neat. The only problem is that the enthalpy change that occurs to go from the constituent elements in their standard state to gaseous ions can't be measured experimentally in one go. We have to break this change down into smaller steps that can all be individually measured by experiment. This is essentially the role of a Born-Haber cycle, to show and arrange all of these enthalpy changes that are needed to go from the constituent elements of a compound in their standard states to gaseous ions, and then to the lattice, and the direct enthalpy change of going straight from the constituent elements to the lattice. Although Born-Haber cycles can look a bit intimidating, if you go one step at a time when working with them and take your time, they can become very useful and, dare I say it, satisfying to solve. For the purposes of this video, we will use sodium chloride as an example to show how a Born-Haber cycle can be constructed. We know we've got two possible ways that we can form the lattice, NaCl solid. Directly from the constituent elements sodium and chlorine in their standard states, enthalpy of formation remember, and theoretically from the gaseous ions of the constituent elements, lattice enthalpy of formation. Clearly the elements in standard states are at a much lower energy than those when as gaseous ions. The lattice formed will be lower in energy than both the gaseous ions and the elements in standard states. We can show this using an energy level diagram, with energy increasing upwards on the left like a y-axis. Our job now is to figure out all the smaller steps we must carry out to go from the elements in their standard states to gaseous ions. Remember, this can't be done in one go. Firstly, both the sodium and the chlorine have to be atomized and turned into single free gaseous atoms. This means breaking apart their bonds to other atoms. For sodium, this would be overcoming the bonding in the metallic structure of solid sodium metal. For chlorine, this would be breaking the covalent bonds between chlorine atoms in chlorine molecules, Cl2. We can measure the enthalpy change for both the atomization of sodium and chlorine, but not together at the same time. We have to break this stage down into two steps, one for each element. Here we have atomized the sodium as it has gone from Na solid to Na gas. Energy is needed for this process, endothermic. It will have a positive enthalpy change, positive delta H, and the combined energy of the sodium and chlorine is increasing, meaning we now show them above the sodium and chlorine in standard states. Next, we have atomized the chlorine as it has gone from half Cl2 gas to Cl gas. Energy is needed for this process, endothermic. It will have a positive enthalpy change, positive delta H, and again, the combined energy of the sodium and chlorine is increasing, meaning we now show them at a higher energy than before. The chlorine has to be written as half Cl2 to start with, as chlorine is in its standard state, Cl2. To form 1 mole's worth of Cl gaseous atoms, we need to start with half a mole's worth of Cl2 molecules. Now the constituent elements are in gaseous state, but we still have to turn them into ions. Just like for atomization, we have to measure these enthalpy changes independently. Here, the gaseous sodium atom has been converted into a positively charged ion by the removal of 1 electron. This is the same as the first ionization energy of sodium. The electron on the right-hand side of the equation comes from the sodium atom. Energy is needed for this process, endothermic. It will have a positive enthalpy change, positive delta H, and again, combined energy of the sodium and chlorine increases. Next, the gaseous chlorine atom is converted into a negatively charged ion by the addition of 1 electron. This is referred to as first electron affinity. This process would actually release energy, be exothermic, and have a negative enthalpy change, minus delta H. This is because the chlorine atom is more stable as a negatively charged ion. Because energy is released here, the combined energy of the sodium and chlorine decrease slightly and so are drawn on the energy level diagram below the charged sodium ion and gaseous chlorine atom. We have now got the constituent elements converted into gaseous ions and have constructed a Born-Haber cycle. We can see the two possible routes of going from constituent elements in their standard states to an ionic lattice in full. By adding in all the measured enthalpy changes for the particular steps outlined, we can find the lattice enthalpy of formation. Using Hess's law, root 1 equals root 2. Well, root 1 is made up of the enthalpy change of the atomization of sodium, positive 107 kilojoules per mole, enthalpy of atomization of chlorine, positive 122 kilojoules per mole, first ionization energy of sodium, positive 496 kilojoules per mole, and the first electron affinity of chlorine, minus 349 kilojoules per mole, as well as the lattice enthalpy of formation. Let's call it delta H here. Root 2 just equals the enthalpy of formation of sodium chloride, minus 411 kilojoules per mole. If root 1 equals root 2, then positive 107 plus positive 122 plus positive 496 plus minus 349 plus delta H equals minus 411. This can be simplified down to positive 376 plus delta H equals minus 411, meaning delta H, the lattice enthalpy of formation, equals minus 787 kilojoules per mole, as minus 411 minus positive 376 equals minus 787. All of the positive and negative signs and brackets can make things look confusing, but by putting the signs and enthalpy changes in brackets and simply adding them together, you are letting your calculator do all of the hard work. You may be shown or taught to reverse the sign of an enthalpy change to go in an opposite direction in a cycle. I recommend against this and find that just following the method shown, directly using the enthalpy values as they are given, massively cuts down the risk of addition errors when totaling them all together. Sometimes further ionization energies and electron affinities needed to be added into a Born-Haber cycle. For example, aluminium chloride is made up of Al3 plus ions and Cl minus ions. To form Al3 plus ions, atoms of aluminium have to be ionized 3 times, each one having its own enthalpy change. First ionization energy to form an Al1 plus ion, second ionization energy to form an Al2 plus ion, and third ionization energy to form an Al3 plus ion. Equally, if the negative ion being formed has a charge greater than 1 minus, more than one electron has to be added to each atom. For example, to form an oxide ion, charged with 2 minus, from a gaseous atom of oxygen, one electron would have to be added to form a 1 minus charged ion, first electron affinity, and then another electron would be added to form a 2 minus charged ion, second electron affinity. The second electron affinity will be a positive enthalpy change, as it will always take an input of energy to overcome the repulsion between the incoming electron and the negative charge that the ion already has. So this is why some Born-Haber cycles appear to have more steps in than others. The same general idea is always the same though, trying to go from a compound's constituent elements in their standard state to gaseous ions. Theoretical lattice enthalpies of formation are based on the ions involved in the lattice. They aren't experimental values that have been measured, unlike the lattice enthalpies of formation determined using Born-Haber cycles. For the theoretical values to work, we have to assume that all ions in a lattice are perfect spheres with only ionic interaction between them. For some compounds of covalent character, values for lattice enthalpies from Born-Haber cycles differ to the theoretical values obtained based solely on ionic attraction data. If the difference in electronegativity between the two ions in a compound is very large, over 2.2 on the Pauling scale, then the ions are in effect perfect spheres and are only held together in a lattice by electrostatic attraction between opposite charges. If the electronegativity difference between the elements in the lattice is smaller than this, then covalent character is exhibited and the ions are held together by both ionic attraction and the slight sharing of electrons, meaning the bond strength, or lattice enthalpy really, isn't purely based on ionic attraction, and the theoretical values obtained start to deviate from related experimental values. We can see this when we compare the theoretical lattice enthalpies of formation of sodium chloride and silver chloride to the lattice enthalpies of formation found using experimental data and the Born-Haber cycle. Theoretical lattice enthalpy based on the ions involved in sodium chloride is minus 766 kilojoules per mole. The value based on the Born-Haber cycle using Hess's law and enthalpy changes from actual experiments gives us minus 787 kilojoules per mole. A very close value. Theoretical lattice enthalpy based on ions involved in silver chloride is minus 768 kilojoules per mole. The experimental value based on Born-Haber cycles from actual experimental data is minus 890 kilojoules per mole. Here, the theoretical value is further from the value obtained using experimental data from a Born-Haber cycle, compared to that of sodium chloride. This is due to the smaller difference in electronegativity between the silver and chloride ions compared to the sodium and chloride ions. A lower difference in electronegativity gives the lattice covalent character, meaning you can't assume only ionic interaction between the ions. As the theoretical value only takes ionic attraction into account, it will give a different value to the one found using experimental data. So, to summarize, lattice enthalpies of formation and dissociation are impossible to measure directly and can only be determined from experimental data using Hess's law. Born-Haber cycles are a type of Hess cycle that show two possible routes for the formation of an ionic lattice from its constituent elements in their standard states. The enthalpies used in Born-Haber cycles are all standard, measured at standard conditions, and have specific names. Standard enthalpy of formation, the enthalpy change when 1 mole of a compound is formed from its constituent elements. Standard enthalpy of atomization, enthalpy change when 1 mole of gaseous atoms is formed from its element. First ionization energy, enthalpy change that occurs when 1 mole's worth of electrons are removed from 1 mole's worth of gaseous atoms. First electron affinity, enthalpy change when 1 electron is added to each atom in 1 mole's worth of gaseous atoms. By substituting actual measured values for each enthalpy change in a Born-Haber cycle, Hess's law can be applied to find the lattice enthalpy of formation. Extra steps need to be added in for ions that have a charge greater than 1 plus or 1 minus. This would be second ionization energy for 2 plus ions and third ionization energy for 3 plus ions, and second and third electron affinity for 2 minus and 3 minus ions. Theoretical lattice enthalpies assume all ions are perfect spheres with only ionic interaction. For some compounds of covalent character, experimental values obtained for lattice enthalpies of formation using experimental data in Born-Haber cycles may differ from theoretical values based only on ionic attraction data. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.